Now let us see the infinite geometric series. That is, this is a very specific situation where we have the geometric progression involving infinitely many terms, and we will see in which situation, although there are infinitely many terms, but the sum of all these terms turns out to be a finite number, right? So let us consider sum of n terms of a basic geometric progression given by, we know that the formula is a into r raised to n minus 1 upon r minus 1, or we can also write that formula as a into 1 minus r raised to n whole upon 1 minus r, that is nothing but Sn. Now what happens is, suppose the common ratio r is numerically less than 1. Okay, so we are considering only a specific condition when the common ratio is less than 1 numerically. So in that case, what happens is, as if you observe the particular term in the formula, that is r raised to n, right? Now as we are talking about infinite geometric series, as we have seen, it means that n, that is a number of terms, approaches infinity because we are taking infinitely many terms. So if n tends to infinity, we can see that r raised to n will tend to 0 because r is numerically less than 1, right? Say r could be 1 by 2 or 1 by 3 and so on. So if a number is numerically less than 1, as we take successive powers of that number, they will give us smaller and smaller numbers. So hence, in the limiting condition, r raised to n will tend to 0. So therefore our formula, when n approaches infinite number of terms, will change to a. Now this r raised to n, since it is approaching 0, the bracket 1 minus r raised to n is nothing but 1, right? So therefore the numerator turns out to be just 1 and divided by 1 minus r. So this is the simple formula for taking the sum of infinite geometric series, but provided the numerical value of r, that is common ratio, is less than 1, right? Now let us see few sums based on the infinite series. Now here we observe that the first term a is 4, and if we see the second term is 4 by 3, so that means the common ratio is nothing but 1 by 3, which is apparent from the given terms. So since 1 by 3 is numerically less than 1, we will say that the sum of this infinite series is finite. So writing the formula of sum of infinite series, we know that it is a upon 1 minus r, right? So a is nothing but 4 divided by 1 minus r is 1 by 3, so that gives us 4 upon 1 minus 1 upon 3 is nothing but 2 by 3. So therefore 2 will cancel with 4 with 2, and 3 will get multiplied with 2. So therefore the answer is nothing but 6. So that is the sum of this infinite series. Let's go ahead and see one more question. Express this decimal number, which is 0.2, and the 34 is the recurring part. So 34 will keep on occurring forever. We have to express this number in rational form. That is, we know that a rational number is a number which can be written in p by q form, where p and q are both integers, where q is not 0, and p and q are relatively primes, that is, there is no common factor in them. So there are two ways. That is, first we will see the shorter and simpler way, which actually does not involve the infinite series formula as such, but we will also see how we can represent this number using infinite series and evaluate the same. Alright. Now to begin with, let us call this required number as, say, x, okay, which is 0.2 and 34 recurring. Right. Now what do we do here is, first we multiply both sides by 10, so that we will get on the right hand side 2.10 34 as a recurring part. Now if we want to obtain the recurring part once again, I will have to further multiply with 100 because there are 2 digits in decimal which are recurring. So therefore if I multiply throughout by 100, I will get 1000 on left hand side, and this gives us 234.34, simply because the 34 is going to be an unending sequence. Alright, now to get rid of that unending sequence, what do I do is I subtract the first equation from second. Alright, so second minus first, so we will get 1000 minus 10 is nothing but 990x is equal to, on the right hand side the decimal part will get cancelled, and 234 minus 2 gives us 232. So hence finally x can be written as 232 divided by 990. So this is a simpler approach, to be frank, where we don't have any formula of infinite series required. Alright, but nonetheless let's see the infinite series approach also. Alright, so here once again the starting step is same, that is we write the given number as x equal to 0.2 and 34 recurring, then 10x equal to 2.34. so this step is also same, but after this now there is slight change. Okay, so let me write this as 10x is equal to, now 2.34 can I write as 2 plus 0.34 recurring, right? So that means it is equal to 2 plus, now if we take 34 common, then what will remain in the bracket is 0.01 as recurring, right? So therefore here we have 2 plus 34, so it means that here we have 0.01 plus 0.0001 plus 0.000001 and so on. So basically when you add up all these numbers you will get 0.01 recurring, right? Now if you look at the numbers inside the bracket, we'll realize that they form a GP because the starting term is 0.01 and it is getting multiplied with itself. So hence as we see that 0.01 is a common ratio which is definitely less than 1, and there are infinitely many terms inside the bracket, so therefore the bracket represents nothing but the infinite series, and its sum can be given by the formula a upon 1 minus r, where a is the first term which is 0.01 upon 1 minus r is also the same, that is 0.01, right? So that in turn gives us 2 plus 34 into, here we have 0.01 whole upon 0.99. Okay, so 0.01 upon 0.99 is nothing but 1 upon 99. So writing that simply, here we have 34 upon 99. Alright, so that further gives us, by cross multiplication, we have 198 plus 34 whole divided by 99, right, which is nothing but 232 upon 99. But if you see, this is equal to left hand side, which is 10x, right? This is equal to 10x. So therefore finally we get, bringing 10 on right, from right to left, we have x equal to 232 upon 990. So this is the same answer as we got from the first process also.